In 1916, just 1 year after humanity gained a new, revolutionary theory of gravity, its brilliant creator made a remarkable prophecy. Delving into the phenomenon of gravitational radiation, he came to a profound realization. Both his newly formulated theory of gravity and Maxwell's already established electrodynamics would inevitably be superseded by another concept: quantum theory. At that time, quantum mechanics was only taking its first, uncertain steps, but the author already foresaw the potential incompatibility of these two fundamentally different views on the universe's basic nature. And, as history has shown, his foresight proved impeccable. However, over a century later, a unified quantum theory of gravity remains an elusive dream. The natural question arises: why? In the following discussion, we will delve deeply into the core of this grand scientific puzzle. We will explore why the fundamental principles of general relativity are unwilling to harmonize with the fundamental tenets of quantum theories. And of course, we will carefully examine one of the two leading contenders for the title of that coveted theory of everything. To truly grasp the multifaceted complexity of creating a unified theory of gravity, it is essential first to clearly understand the true meaning of the term theory. It is surprising how often people use this word in everyday speech without truly delving into its deep, scientifically grounded meaning. One often encounters statements like, "It's just a theory," or "Scientists don't have a complete understanding, because a theory is something far from true reality." However, in reality, a scientific theory represents the most accurate and comprehensive description of reality available to us at the current moment. In common parlance, the word theory might indeed be associated with a synonym for guess, meaning something that has not received sufficient confirmation. But in strict scientific discipline, the situation is diametrically opposite. A theory is not based on conjecture or hypotheses. It relies entirely and completely on undeniable facts. Using a meticulous scientific method, a theory aims to interpret these facts, for example, to provide a comprehensive explanation for a particular natural phenomenon. In a simplified form, this process looks something like this. A researcher makes a certain observation, then develops a hypothesis designed to explain that observation. Then, they carefully construct an experiment to test and confirm their hypothesis. If the experiment does not yield the expected confirmation, the scientist develops a new hypothesis, and the entire cycle repeats. If the hypothesis does find confirmation in the experimental results, then, contrary to popular belief, it is not yet elevated to the rank of a theory. It must undergo multiple repeated checks, and only when it withstands criticism and is not refuted by other, more precise and perfect experiments, only then can this hypothesis be integrated into an existing, broader theory or even become a cornerstone for building a completely new concept. Therefore, a scientific theory is meticulously verified knowledge that has passed countless tests and brilliantly explains the phenomena we observe in the world around us. Moreover, it possesses the unique ability to make predictions that ultimately find empirical confirmation. A prime example is Isaac Newton's classical theory of gravity, which described the motion of planets and the process of objects falling to Earth with astonishing accuracy. Its predictions formed the basis of all modern rocketry, enabling humanity to launch spacecraft to distant celestial bodies. Similarly, the theory of electromagnetism describes in detail the motion of charged particles, the emission of electromagnetic waves, and their propagation in various media. And thanks to its ingenious predictions, we possess all the benefits of electricity, from communication systems and radio waves to lasers, smartphone screens, and high-speed fiber optic internet, as well as many other technological marvels. In fact, scientific theories have become the foundation upon which the entire life of modern civilization rests. Thus, a theory is not merely a speculative assumption. It is a powerful tool that constantly helps humanity live better and develop. Of course, in the scientific world, there is always the possibility of new data or evidence emerging that may be incompatible with an existing theory. In such cases, the theory is either substantially refined and improved or replaced by a more comprehensive concept that provides a more accurate and complete explanation of reality. The longer the central, key elements of a theory are preserved, The wider the range of observations it can predict, the more rigorous tests it successfully passes, and the more facts it can convincingly explain, the more robust and reliable it is. In modern physics, two such phenomenally successful examples are the general theory of relativity and the Standard Model, which describes elementary particle physics. It would probably be fair to call them the two greatest theories in the history of science. The first of these, proposed over 100 years ago, still remains our most perfect form of a theory of gravity, applicable at the macro level. Although its detailed consideration has been discussed previously, it is important to emphasize again, general relativity has withstood absolutely every test to which it has been subjected. From the most delicate laboratory experiments to the grand scales of celestial mechanics, gravitational lensing, gravitational redshift, the formation of the large-scale structure of the universe, and finally, the direct detection of gravitational waves, this theory has never failed. However, it is important to realize that the gravity we observe and describe manifests at scales where humans, planets, stars, galaxies and their colossal clusters exist, as well as all familiar objects, from the most mundane items to grandiose cosmic structures. But as soon as we reduce the scale to the level of atoms and elementary particles, serious difficulties arise. In fact, scientists are not even entirely sure that gravity acts on these microscopic entities in the same way it does on planets. Elementary particles are so infinitesimally small, and their masses are so negligible, that directly measuring gravitational interaction between them currently appears practically impossible. At least, what is known for certain now is that all these electrons, protons, neutrons, atoms, and molecules are somehow held together, preventing our bodies from disintegrating into tiny fragments and preventing us from falling through the Earth's crust to its scorching metallic core. This means that at such tiny scales, other forces dominate, whose influence becomes incomparably, many times greater than gravity. These forces, or more precisely, fundamental interactions, have been studied quite thoroughly. The electromagnetic force, for example, causes an electron to be attracted to an atomic nucleus. The strong nuclear force reliably holds the atomic nucleus together, and the weak nuclear force plays a key role in nuclear fission and nuclear fusion processes. And it was to comprehensively describe all these phenomena that the Standard Model of particle physics was developed, which is based on the principles of quantum field theory. One of the cornerstones of this theory is the postulate that each fundamental interaction is realized through the exchange of special particles called bosons. These bosons essentially act as intermediaries or carriers of interaction between two interacting particles. As an illustration, consider the quarks confined within protons and neutrons. They exchange a specific boson responsible for the strong interaction, which is called the gluon. The boson mediating the electromagnetic interaction is perhaps best known to the general public. It is the familiar photon. Thus, the sum of fundamental interactions affecting charged particles can provide an exhaustive description of everything imaginable in the microcosm under any given conditions. Indeed, the Standard Model is a theory no less successful than general relativity, as all its predictions find convincing confirmation in experiments, from observations of radioactive decay to results obtained at the largest particle accelerators. Its ultimate test and simultaneously grand achievement was marked by the discovery of the Higgs boson, which, as is known, gives mass to elementary particles. However, a natural question arises: what is the position of gravity in this elegant picture? At first glance, it might seem strange to consider a theory completely successful if the crucial particles of nature, which are supposedly the carriers of the fundamental phenomenon of gravity, have not yet been discovered. Nevertheless, for the Standard Model itself, this circumstance is not a problem at all. It effectively does not account for gravity, because, compared to the three other fundamental interactions of nature, gravity is not just the least strong, it is absurdly negligible, practically insignificant at the scales of the microcosm. Consequently, ignoring gravity does not hinder an extremely accurate description of particle behavior in the vast majority of situations. Well, almost all. And these become a source of serious difficulties for the scientific community. The fact is that not all the smallest objects in the universe have small mass or insignificant amounts of energy. Phenomena occurring in the central regions of black holes or at the very beginning of the universe represent those phenomena that cannot be adequately described by either general relativity or the Standard Model. Scientists are simply unable to calculate the behavior of gravity at microscopic scales and at extremely high energies, especially near singularities. At the same time, if there is a quantum gravitational field, its behavior under certain circumstances remains completely unclear. Thus, even with two outstanding, exceptionally accurate, and reliable theories explaining the vast majority of phenomena in the universe, this is still not enough. Physics remains incomplete, literally not whole in every sense of the word. It should be understood that calculating the behavior of particles in curved spacetime is entirely possible. Of course, the mathematical apparatus becomes significantly more complex, but in such a case, the question simply boils down to having sufficient computational power. However, this is only an approximate solution that in no way eliminates the problem of singularities. When spacetime curvature reaches extreme values, existing approaches become powerless. And even with strong desire, ignoring this fundamental problem is impossible. So-called quantum gravity is not just a theory explaining how gravity works. It is a grand project aimed at unifying all of physics into a single, consistent system. This is why every theoretician realizes that as soon as they successfully integrate quantum theory and general relativity, all that will be left for them is to buy tickets to Stockholm, where the Nobel Prize awaits. In general, the incompatibility of these two great theories stems from several key differences, each of which, unfortunately, is of colossal importance. For example, general relativity is, in a mathematical sense, a classical theory. This means that all physical quantities, such as the velocity and position of certain particles, as well as the strength and direction of various fields, take specific numerical values. That is, any physical quantity can be expressed by a precise real number. For example, a speed of 10 meters per second, a mass of 80 kilograms, and so on. It is in this context that general relativity is considered a classical theory. However, the problem is that theories describing the behavior of particles at a fundamental level are quantum theories. And in quantum theories, physical quantities generally do not have definite, fixed values. For example, the position of an electron can be measured with any desired degree of accuracy. But this inevitably leads to a loss of certainty regarding its momentum, and therefore its velocity. Or, conversely, a precise measurement of momentum will deprive the researcher of certainty regarding the particle's position. That is, a certain degree of uncertainty is always present and cannot be avoided. Thus, in quantum theories, the properties of particles are not strictly defined. Instead, they are described by so-called wave functions, which provide not a specific numerical value, but only a range of probabilities. However, these are merely precursors to the real difficulties, as the true problem of incompatibility is much deeper and more dramatic. The essence is that in quantum mechanics, space is perceived merely as a passive background, a kind of receptacle, container, or, if you will, a stage on which all the fascinating interactions between elementary particles unfold. In other words, spacetime is not a physically significant entity. It is only necessary for all physics to happen. On top of it. But if for quantum theory spacetime is just a backdrop, in general relativity it is the main character, the key actor. In this extraordinary theory, spacetime itself acts as the entity that creates the entire show. After all, it is its curvature that gives rise to the physics of gravity. And this is where a truly colossal barrier arises, one that no one has yet been able to overcome. In fact, it remains unknown whether it is even possible in principle to overcome this fundamental conceptual difference, as all attempts undertaken so far have invariably ended in failure. Mathematical calculations yield very strange, sometimes absurd results, which scientists try to circumvent, often resorting to crude mathematical constructions far from the real physical world. The question of how to proceed gives rise to many completely different conceptual directions. For example, string theory, which will be discussed in detail in a later section, seeks to create a unified description of all four fundamental interactions from scratch. Thus, proponents of this approach aim to fundamentally rethink the universe to resolve long-standing physical mysteries. Other concepts appear more moderate. In particular, a number of theorists prefer not to create an entirely new paradigm, but instead focus on finding ways to harmonize general relativity with quantum theory. Consequently, the task of creating a unified theory of gravity can take on different meanings for different researchers. What seems like an obvious solution to some may prove insufficient for others. This circumstance provides a vast field for philosophers of science. Nevertheless, if a researcher were a theoretician, they would likely choose the first, most logical path, the quantization of general relativity. This implies viewing spacetime not as a single, continuous structure, but as a discrete entity composed of individual elementary units, quanta. Why is such an approach considered logical? The reason lies in the fundamental incompatibility of quantum and non-quantum systems. A prime example is the famous double-slit experiment, which best demonstrates the paradoxical behavior of elementary particles, inexplicable within classical physics. When protons are directed through two slits, an interference pattern of dark and light bands forms on the screen behind them. This indicates the impossibility of precisely determining which slit a particular particle passed through. Physicists interpret this phenomenon as the proton being in a state of superposition, meaning it passes through both slits simultaneously. Truly, this is a very unusual property of the microcosm. If a particle has mass, and a proton, as is known, is a massive particle, then it must inevitably generate a gravitational field. Therefore, if gravity behaved within the framework of classical physics, one could set up a detector and accurately measure the location of this field. In other words, the gravitational field would unambiguously indicate the particle's precise position, allowing one to clearly determine which of the slits it passed through. However, as noted earlier, certainty regarding precise physical parameters is not characteristic of quantum particles. This paradoxical situation convincingly demonstrates that gravity, whatever its nature, cannot be an exclusively classical quantity, at least in the domain where quantum mechanical effects are manifested. Secondly, the logic of quantizing gravity is also due to the fact that a similar approach has already demonstrated its effectiveness, though not in relation to the gravitational field, but to other types of fields. As an example, one can cite quantum electrodynamics, an extremely successful unification of quantum mechanics and relativistic theory. Special relativity is integrated into every equation of quantum electrodynamics. As a result, the electromagnetic field is considered quantum, meaning it consists of discrete particles called photons. Consequently, any charged particles entering this field experience its effects through the exchange of these photons, which, incidentally, are called virtual. However, despite this success, numerous attempts to quantize gravity in a similar manner have been unsuccessful. The reason lies in a fundamental difference. The electromagnetic field is a real physical field, meaning a tangible physical entity that exists and propagates in space and time. The gravitational field, according to general relativity, is spacetime itself, or more precisely, its geometric property. It is no coincidence that the term unified theory of gravity is more often used in this context rather than quantum gravity, to which readers may be accustomed. This is because not all unification concepts specifically involve the quantization of spacetime. For example, physicist Jonathan Oppenheim is a well-known proponent of an approach that is neither quantum nor classical gravity. He explores the potential for creating a more fundamental concept that would combine the characteristics of both approaches without being either in its pure form, a kind of hybrid solution. Oppenheim continues to develop his theory, but like the vast majority of others, it requires further refinement and, of course, experimental confirmation. Nevertheless, one should not assume that there are no promising developments currently. On the contrary, today there are at least two theories that could potentially claim the status of a theory of everything. One of them, of course, many have heard of, string theory. The second, loop quantum gravity, attracts somewhat less attention. As already mentioned, string theory will be discussed in detail in the next section, which will allow for a more complete presentation. Its competitor, loop quantum gravity, will be examined immediately. First and foremost, it must be acknowledged that both of these theories represent a vast body of extremely complex mathematics, the comprehension of which is very difficult for a non-specialist, such as the author of this text. In the language of mathematics, any physical theory often appears much more elegant and appealing than when explained verbally. Therefore, when physicists strive to find an understandable interpretation of their mathematical formulas, the result is not always accessible to a broad audience. Moving forward, only some key aspects of loop quantum gravity will be presented, which seem to deserve special attention. First, this theory eliminates a key conceptual contradiction that existed between the quantum world and general relativity, namely, the very idea of a background spacetime continuum. There is no longer a need to consider its shape or the values of various fields within it. The need to refer to a specific coordinate system for the equations to work correctly also disappears. Loop quantum gravity, LQG, effectively postulates that no original background spacetime continuum exists at all. What we perceive as spacetime is actually the result of complex quantum interaction. This is how loop gravity theory currently represents scientists' most successful attempt to quantize general relativity, that is, to apply quantum principles to the spacetime continuum itself. This idea is realized through a specialized mathematical tool known as graphs. This structure resembles a network consisting of discrete elements, called vertices or nodes, and connecting lines, called arcs or edges. This is akin to the representation of molecules from high school chemistry courses. Within loop theory, this network is called a spin network, and it regulates how the elementary cells of the spacetime continuum are interconnected. The smallest discrete point of space here is represented by nodes, and the edges symbolize the quantum connection between them. Thus, one can approximately imagine the spacetime continuum at its smallest scale. It is extremely important to emphasize that the spin network cannot be further divided into anything smaller. In the context of general relativity, the spacetime continuum is a continuous medium. This means the possibility of infinitely decreasing the scale, similar to limitless image scaling. However, in loop quantum gravity, such an approach is impossible. Sooner or later, a limit is reached, a kind of smallest pixel that cannot be magnified. LQG asserts that the smallest possible volume is determined by a fundamental scale on the order of the Planck length, which is 10 to the minus 35th power of meters. To grasp this scale, imagine this: if such a minimal cell were the size of a grain of sand, then an atom compared to it would be the size of an entire galaxy. It is difficult to even imagine what it means to experimentally confirm the existence of an object so minuscule. Now, the curvature of the spin network, caused by the presence of mass, for example, an elementary particle, is what we interpret as gravity. A spin network evolving in time is called spin foam. This represents the quantum mechanical dynamics of the spacetime continuum. This is how the main idea of loop quantum gravity is formulated. Everything around us is discrete, consisting of tiny grains, and the spacetime continuum is no exception. But what are the consequences of such an approach for the real universe? The first and most significant result is the resolution of the problem of singularities. They simply do not exist in this theory. As is known, singularities are vulnerable points of the two main physical theories, places where physical parameters tend towards infinity. Although in reality, infinity means that modern physics simply cannot explain what is happening there. Loop quantum gravity elegantly resolves this problem because it establishes a fundamental limit, the Planck density, beyond which matter is unable to compress further. What this means in practice is not yet entirely clear. There are two main hypotheses. Either this tiny point is stabilized by some exotic form of matter that never undergoes gravitational collapse, similar to degeneracy pressure in neutron stars, or the energy density reaches such critical levels that a rebound occurs, potentially leading to the formation of phenomena like white holes and other unusual concepts. In either case, it follows that no singularity existed at the moment of the Big Bang itself. This is already a truly significant conclusion, as it leads to a fundamentally new picture of the universe. So-called loop quantum cosmology asserts that there was no actual genesis of the universe in the conventional sense, where before this event there was nothing, either space nor time. In reality, quantum cosmology posits that the universe has had an infinite existence, but periodically contracts to a minimum permissible volume, and then returns to the expansion phase observed today. Yes, this is the Big Bounce concept, which you may have already heard about. At first glance, such an idea might seem nonsensical, as it is widely believed that the universe will not cease expanding and will do so indefinitely. At least, that has been the interpretation of current observational data. And if this were written a month ago, that is precisely what would have been stated. However, the situation turns out to be far more complex. Preliminary data has recently been obtained from a new extensive astronomical sky survey, during which astronomers measured the redshift values of millions of galaxies across the universe. Their data suggests that dark energy is not characterized by a constant density. That is, its influence appears to evolve over time. This implies that the rates of expansion could undergo changes, and the further evolution of the cosmos remains uncertain. The universe might begin to expand even faster or, conversely, transition into a phase of contraction. It should be specifically noted that, at present, these are only preliminary findings, and it would be premature to regard them as a definitive discovery. However, if the variable nature of dark energy is indeed confirmed, it will lead to significant changes in cosmology. Indeed, theorists working on loop quantum gravity have achieved significant progress in developing a viable alternative to string theory. However, their own theory remains incomplete and may ultimately prove inapplicable to describing the real universe. This naturally raises a crucial question: why, despite all the identified limitations of loop quantum gravity, do the vast majority of physicists consider string theory to be the most promising attempt at a theory of everything? What are the fundamental differences between these two approaches? And what specific fundamental problems does string theory aim to resolve?